Hi everybody, this is David Paul and we're here to have a webinar on the basics of conductivity. And it'll be Sherlyn, for those of you that have been to any of our other webinars, the last 3 webinars, Sherlyn has been the instructor from Yokogawa. So for those of you that haven't been to any of the previous webinars, Yokogawa is a huge global company and it's over 100 years old and is active really in all sectors, so I'm sure active in your sector. David H. Paul Inc., we are the world's leader in water treatment training, high-tech water treatment, basically any water treatment technology. So lots of different training products and also lots of different technical services. So we have joined with Yokogawa to give a series of 5 webinars, and we are on the 4th one for Conductivity Basics, and we've been doing it every 2 to 3 weeks at this day of the week and also this time. So the format's always the same. It's about a 45-minute presentation. I'll give just a few minutes of intro, and then Sherlyn provides the details on conductivity, and then we shoot for 10 to 15 minutes of Q&A. So at any time, please type your questions into the questions chat box. We will record this. It is being recorded right now, and it will be available at our website as all of our webinars are. And tomorrow or Monday, you'll receive an email and it will give you a PDF of this presentation and also the link to the webinar. So just to make sure that you're aware that Yokogawa and David H. Paul Inc. do not have a financial relationship. We're not endorsing or promoting each other's products. We're simply providing this information as a service to our clients. I've been in water treatment for 40 years. Been in hundreds and hundreds of plants, master's degree in microbiology, and also through David H. Paul Inc., the highest level of certification. Sherlyn is with Yokogawa, and she's the process liquid analyzer product manager, and she's been with Yokogawa for 9 years, has really good previous experience, and has really good education as well. So again, if you have a question, input your questions. We'll cover as many questions as we can during the Q&A session at the end. Any questions that we don't get to today will be answered by email, and then the questions and answers will be added to the recorded webinar. So let me just do a real brief overview of conductivity more on the practical end. Conductivity meters measure ions. Ions are charged atoms or molecules, and I think it's really important to realize that conductivity meters only measure ions. They aren't going to measure uncharged contaminants. So you can have low conductivity, and potentially you could have high levels of uncharged contaminants, because again, the conductivity meter cannot read those. Conductivity is expressed as microsiemens per centimeter or micromole per centimeter. We'll use the microsiemens. So here's a list. In the blue, you have positively charged ions called cations, and you see that they're going from +1 to +3 charges. And then the purple ones over on the right are anions, negatively charged ions. And the first 5 are atoms, so they're charged atoms, and then the last 4 are charged molecules. So in this reaction here, we see silicic acid. Well, silicic acid is a weak acid, so it is mainly not dissociated, which would mean it was uncharged. So a conductivity meter would not measure silicic acid, but the little bit that ionizes, the bisilicate ion, would be measured by a conductivity meter. The same thing, calcium carbonate would be uncharged, but when it dissociates, into calcium plus carbonate ions, then the calcium and carbonate ions would be measured by a conductivity meter. And then again, we can also have charged molecules. In this case, we see that acetate ion on the far right is charged, so it would be measured by a conductivity meter. So contaminants can be divided into dissolved, these would be very tiny, and suspended, these would be particles. We can subdivide dissolved contaminants into charged and uncharged. We can subdivide suspended contaminants into living and non-living. RO membranes do a phenomenal job of rejecting just about everything. So we likely will get 98, 99% rejection of charged contaminants. We'll get almost 100% rejection of particles. And it's only because the membranes aren't perfect that we don't get 100%. But we'll still get 99.9, 99.99% rejection of viruses, which are some of the smallest particles. So it's almost 100%. The one area where we can get some things that slip through the membrane are the uncharged contaminants. So the dissolved gases go right through for the most part. So for example, CO2, dissolved carbon dioxide, would basically have zero rejection, so it goes through the membrane. Other things other than the gases, it just depends on the molecular weight. So the larger the molecular weight, the higher the rejection. So downstream of your RO unit, your biggest contaminant is going to be CO2 related, because CO2 goes to the membrane, but then it's converted because of the pH of the permeate. It's going to convert into mainly bicarbonate ions. So the carbon dioxide would not be measured, or the carbonic acid also would not be measured by a conductivity meter, but the bicarbonate and carbonate ions would. So this rectangle is going to represent an RO unit, and that line is going to represent the membrane inside an RO unit. Feed water enters the RO unit. Due to the pressure, water passes through the membrane and becomes permeate or product water. What doesn't go through the membrane exits as concentrate, brine, or reject. Because of CO2 going through the membrane, you'll see that permeate pH is going to be lower in almost all waters than the feed, and the concentrate will have a little higher pH, and that's due to CO2 going through the membrane. There is no strict conversion factor for natural waters to convert from conductivity to total dissolved solids, but in the field, the conversion factors that I use, 0.6 for the feed, 0.5 for the permeate, and 0.7 for the concentrate. And this is just showing that the permeate disproportionately, because it has smaller ions and faster ions, hydrogen is the fastest ion and the pH is lower, so there's more hydrogen. So you have more conductivity per milligram per liter in the permeate than you would in the feed and the concentrate. So that's just a real quick overview of conductivity. And now I'm going to turn it over to Sherlyn, and Sherlyn will handle the rest of the presentation, and then I'll come back for the Q&A session. Sherlyn?
Hi, okay, thank you. All right, let me show my screen real quick, guys. And do this. Alrighty, so basically we've done, like you said, the pH and everything. So I wanted to take a moment, because sometimes conductivity measurements, you have them in your plant. They're just forgotten about because they normally work without maintenance headaches for the most part. So I wanted to give a practical understanding of the strengths and limitations of conductivity as a whole. So I wanted to tell you about the differences in measuring conductivity if we're doing that, or if we're doing very ultra pure water where we may use it as resistance or resistivity reading, and then also go and explain the difference between the two types of measurements, because you may also have, like on your mixed bed or your ion exchangers, your you may have your polishers, you may have percent concentration readings up there on your regen line. So talk about the difference between contacting and inductive, the two terms that are used for how to measure conductivity. And then talk about what we have seen for cleaning and calibration best practices over the histories of Yokogawa. And then talk about what we, again, if I have seen a problem, the troubleshooting that I've seen at the installation sites that can give you a headache, and then things for you to possibly check. So first, let's talk a little bit about theory. Why do we measure conductivity? Conductivity is a key measurement and control parameter in a wide variety of applications. It can be used as an alarm point, and what we've also seen it as, sometimes there are applications where we're measuring pH, or we have been measuring pH, and we get a lot of headache, but we've learned that we can also measure conductivity and kind of infer the same pH reading, and we have less maintenance with it, and it gives us less of a headache. So sometimes we have applications like that. So high level, when we talk about water, anywhere there's water, whether it's municipality, whether it's plant, whether it's your wastewater treatment plant, you're going to have conductivity readings. And for the most part, like the pH and conductivity will be measured at the exact same time to kind of give you to determine like the quality, water quality as a whole. But for the most part, you're going to have more conductivity readings than you would pH readings on a sample line. So like, say example, your boiler feed water. You will have one pH coming off of a line, but then you're going to have what we have specific conductivity. Then that sample will run through a cation, like a resin bed, a cation bed on your panel probably. Then you have, after that resin bed, you'll have it called cation conductivity, and then that sample may go from there, and it may go through a reboiler, and you'll have what's called degas conductivity. So you have 3 conductivity measurements for the most part to your 1 pH. So you have more, you just don't have to maintain them as frequently. Again, so in power plants, you're going to have your boiler feed water, you're going to have your boiler blowdown. So as you're scaling your increases, that conductivity value will increase to a threshold where it'll indicate, okay, now time to blow out all of the junk left over in our boiler drum. Cooling towers, condensate return, you're going to have conductivity readings. But those are just for more like water quality within a plant or a process, right? However, there are applications where they do beyond just water quality. They actually use conductivity, like in pulp mills, the black liquor or green liquor, to indicate quality of the pulp stock or the water in the pulp stock, or like a bypass. I'm lost for words at the moment, I'm sorry, but you make the process and it's the reject, I guess, for lack of better words, that's going to go in somewhere else to get cleaned up. So there are other places to use conductivity. So let's start with a basic definition of what conductivity is. It's basically defined as a solution or a substance, so a solid's ability to carry or conduct an electric current. An electric current will flow through certain solids and liquids when a voltage difference exists between 2 points. So say a solid such as copper that's used to make circuit boards, it will actually, if a current is placed on it, flow will generate and actually be carried through an electron charge transfer through the atom structure itself. With liquid, it's a little different. Like he said, David said, it is actually has to have presence of ions in a sample, and that's what carries that electric current from one point to another. So if there's no ions present in a solution such as ultra pure water, then there's no current that can flow, so a solution's not conductive. So in this example here, we're just showing, say, table salt in a beaker, solid salt with a voltage, a battery, put on it. It doesn't carry a current through the salt by itself, so it can't light a light bulb. If we dissolve that salt into water and we apply a current, it will create a voltage. It will create, it'll be able to light a light bulb in this little example here for imagery. Same thing can be said about different chemicals. And the higher the conductiveness of a chemical, the higher the voltage reading, the analyzer can actually read that. So that's what we're measuring. But one thing we have to take a moment and think about, not just from a safety standpoint, But this is a snippet of, does anybody remember that ALS bucket challenge that went around in 2014, 2015? Even our tap water out of our fire hydrant, out of our water, has ions present. So we have to be cautious when we take water around electric devices, devices that have electricity running through them. Unfortunately, the firefighters in Kentucky did a huge ice bucket challenge, and the water vapor itself, just the vapor, made contact with the power cords hanging above them. Well, that current from the power cords traveled all through the water vapor, all through the water ions, and actually a firefighter was electrocuted. So we just have to be careful when we're water and we have electric currents. So what's the basis for measuring conductivity, or what we consider conductiveness of a liquid? It begins with using Ohm's law. So Ohm's law states you have a voltage, which is the current is the result of the amount, the voltage in a circuit, a whole electric circuit, is the result of the amount of current, which is the I in the equation, multiplied by the amount of resistance of the solution, for lack of a better word, and then our sample, in the circuit itself. So here we're interested in seeing how conductive a solution is. We actually have to rearrange the equation, and we calculate basically we calculate and find the resistance of the solution, and then conductivity is just the inverse or the reciprocal of resistivity. So that's why we can actually measure conductivity or resistivity in the same analyzer with the same sensor, because it's just a multiplication factor in the analyzer itself. And then, like David said, there's different units of measure. So we have most commonly microsiemens to millisiemens to Siemens, and then for resistivity we'll do the ohms, mega ohms. Here is just a sample of the scale. Full scale goes from 0 to 2 million microsiemens. And sorry, let me get a sip of water real quick. When we look at a solution, we see how conductive it is. Again, we have to look at what ions are present in there. Is there calcium? Is there sodium? Is there chlorides? Are there hydrogen ions? Are there hydroxyl ions? Because that's what's responsible for carrying an electric current. Conductivity is simply a quantitative measurement for every ion that's present in there. It's not particular, and we cannot distinguish and tell you how many sodium ions are present versus something else. So I just have to be cautious of what and know exactly what we're measuring when we measure the scale, when we measure conductivity. And this is just going to show you an example. I can't tell you when I read a solution if it's 1,000 microsiemens on my analyzer, if I'm in milk or if I'm in something that could be very deadly and poisonous. Same thing when we're looking at those percent concentrations on the our polishes and our mixed beds, our cation bed and our anion bed. I can't tell you if we've got sulfuric acid or if we've got hydrogen, sodium hydroxide. So this is just a sample of the curve. So chemicals or have a curve that is, depending on the concentration, the conductivity value will increase, and then sometimes it will actually also decrease because of the mobility of the ions. So here, at a certain point when you're in the lower range, sometimes we may use pH measurement along with conductivity to know, okay, is this 50 millisiemens I'm seeing, is it because of sulfuric acid or is it because of, my base, my alkaline solution? So we just need to know exactly what we're measuring. And we'll show you in just a moment, I'll show you why. There are 3 key things that we have to look at when we look at conductivity as a whole and percent concentrations in particular. Each chemical responds differently has a different conductivity concentration curve than the next. So they may be similar, but they peak at different points. Again, I said it's non-specific. If you've got a mixture of solutions, I can't tell you what one is over the other when we look at conductivity and we use it as percent concentration in the analyzer. Temperature is the biggest factor of conductivity value. If temperature increases, the ions will move faster and make continuity in our sensor cell that I'll show you in just a little bit, and I'll get a higher false high reading than it actually is just because of the temperature. And then the same thing with the the size of the ions. So here is a curve of concentration. Look at the hydrochloric acid there. I have two conductivity readings at the exact same point, but they're related to two different percent concentrations. This is because of the ions themselves actually have a decrease in conductivity value once they hit a certain threshold point. Some percent concentration curves have more than one peak. It could even go back up. But we just have to know where we are on a curve. So if we're trying to measure over a peak for percent concentration, it'll give us difficulty. But what happens a lot of times is we know where we're starting from, and we kind of pair the conductivity reading up with, like I say, a flow meter and a timer, and we know I've been pumping for X amount of time, so when I see the conductivity value first, I know I'm on one side of the curve, and when I see it the second time, I know I've gone up over the curve and I've come back down. So it's just something to be aware of if we're using conductivity for percent concentration readings. So again, here are the three things that affect conductivity the most. The concentration of the ions. The conductivity itself will increase proportional to the concentration, providing that the mobility of these ions is not affected. So the mobility of the ions, the size of the ions themselves, affect the conductivity reading as well. Smaller ions are more mobile than larger ions. So if we've got something that's got larger ions and we're in a higher concentration of a solution, we need to make sure that we're picking the correct instrumentation for that type of measurement. And then again, the temperature. The higher the temperature, the ions move faster, so we get more continuity, so we get false high readings. A lot of instrumentation, and most everybody in conductivity especially uses what we call temperature compensated. Everything's normally compensated automatically back to room temperature, so 25C or 77F, and it's because of this effect. In pharmaceuticals, they have to actually report and calculate uncompensated values. So there are some instances where you wouldn't do temperature compensation, but for the most part you will do temperature compensation. So how do we actually measure conductivity itself besides the calculations that are done in the analyzer? There are two different types of conductivity sensors that are available today. One is the term contacting. This means that it is made of a sensor that physically the measuring elements come in contact with the process. The other term is inductive, electrodeless, or toroidal. These are sensors that are more donut shaped, and I've got pictures in just a moment, that are covered with Teflon and or PEEK material, and it's the measurement elements themselves do not come in contact with the process, so they consider them electrodeless. And it's all conductivity, it's just a matter of how it actually happens. So let's look at contacting conductivity. How does it work? Basically, the way it works is a voltage is applied. You have two measuring elements, or you could have four measuring elements in one sensor, and an alternating current is applied to the measuring cells. It goes back positive, negative, and the ions will move their particular charge, obviously like attracted to itself, and alternate back and forth. The ratio or the speed at which these ions move back and forth and make continuity with the measuring elements is proportional to a conductivity reading. So there are problems or concerns with contacting conductivity that we have to talk about, that we have to consider. If we put a sensor that's not meant for a high conductive solution in a high conductive solutions, the ions will be, there'll be too many present that they won't be able to get continuity between the two, and it will have an effect what we call polarization. And I have a photo and a couple slides of that. So we have to be aware with what we call a cell constant when we talk about contacting conductivity. Okay. The way inductive conductivity works is, think of it as a like a transformer. you have two identical matched coils side by side each other inside of a donut body for the most shape. This is probably the industry standard style. There are some that are like a flow-through pipe that have it as well, but it's the same kind of idea. You have two coils. One generates a magnetic field. The process passes through the donut, picks up this electric charge, the ions in the solution, and then it drops it off, how much it picked up, on what we call the receive coil or the pickup coil. And that ratio and how much is picked up and dropped off is proportional to how concentrated the conductivity value is. So whether you use the donut shaped, that's like this, or you use the flow-through pipe style, it has the same thing. There's a drive and a receive coil. The process simply flows through it, and the proportion in which it picks up and drops off is proportional to the conductivity reading of the sample. The one main disadvantage with these inductive style sensor is the sensitivity or the accuracy if you go below, say, 50 microsiemens. Most of the accuracy statements are 0.5% plus 1 microsiemen. If you're in something that's 50, 60, 100 million, not 100 million, like 100,000 microsiemen solution or 1,000 millisiemen solution, that one more microsiemen is not going to make a big difference. But if you're in pure water, ultra pure water, where you're less than 1 microsiemen, a accuracy of adding 1 microsiemen is a big influence to you. So when do we know what to choose and where to choose where? You have the exact same kind of setup that you have with pH. You have some analyzer, some sensor with a cable, and some holder. When we get into sensor selection with contacting, there are two styles that I mentioned. You have what we call a 2-electrode, and we have what we call a 4-electrode. There are advantages of using 2-electrode. You're going to use those most likely. They have the highest accuracy in ultra pure water, low conductivity values. If you're using contacting and you're in something that has a high conductivity value, you're not going to want to use a 2-electrode system. You're going to want to actually use a 4-electrode, meaning there's physically 4 measuring elements in the same body. So in this picture here with this either stainless steel or this like the maroon brown one there are 4 measuring elements that the current is alternating between, that the ions can freely move and make contact with. So you have more surface area for larger samples that have larger ions present in them, like more concentration of ions present to make contact, so you get more accuracy, better accuracy with higher conductivity readings. Another style is like this one here is the Hamilton one. You can kind of see it on here, but it has the peak material at the bottom, and then it has like a metal pole. On this side we can only see 2, but on the other side there's 2 more. So those poles is the same thing as what would be inside those other sensors that have the ions that respond and react, that we can generate and read the voltage that's generated. And then you have the triode or the electrodeless is the donut. Again, what happens is with the contacting, you have to make sure you have the right cell constant with chosen for your application, and I'll show you that in just a moment. And with inductive, there is only one sensor for the most part. So contacting, we're more cautious, and we have to be aware of what our measurement range is to make sure we pick the right cell constant, the right contacting sensor. With inductive, if anything over 50 microsiemens, if you can put an inductive in, you're going to get virtually no maintenance because it's has made of a different material. It's got PEEK and Teflon. So here's just the little differences between contacting and inductive, right? Again, the contacting sensors physically come in direct contact. So if there's anything that could cause corrosion on your titanium or stainless steel, you're going to have to pay attention to that. You're going to have to change them out. You're going to have to clean them. If you've got a chemical that may attack stainless steel, you're going to have to make sure that you use a sensor that's made of a material that your process can handle. So they do require a little bit of maintenance, but for pure water, there's not that much maintenance that you have with them. And inductive, like I said, because there are one sensor that does the whole range, we don't have to pay attention to which version we select. You just have to choose most commonly between either PEEK material for your process or Teflon material for your process. The biggest headache with inductive is because it does generate a magnetic field. It is larger in size. We got to make sure that it has enough room to install it in the pipe so that the pipe doesn't interfere with that magnetic field, which would cause measurement errors for us. So I created a little cheat sheet for you guys to reference if you have any, in the future if you need it or anything, but where we recommend using contacting versus inductive. And basically anywhere you can put your inductive, you'll be happier overall. And then here's some more comparisons for you guys to reference when it comes to your contacting conductivity, because remember I said there's a difference between 2 electrode and 4 electrode. 2 electrodes, the strengths of using that type of system is you have higher accuracy at the ultra pure water. With 4 electrodes, if you have applications that are fouling that you don't have enough space in your process to put an inductive sensor, you need to put a 4 electrode over a 2 electrode. Weaknesses are they do have cell constants, so they are specific for certain measurement ranges only, so we have to be aware of that. And then any aggressive chemical attacks, we got to make sure that we choose the right material of construction. And I keep saying there's something about a cell constant and measurement ranges. I only have for me reference point what our sensor's measurement range is, but every particular contacting sensor, doesn't matter who the manufacturer is, each sensor has what we call a cell constant. This cell constant is, is just a multiplication factor in the analyzer. So when we're measuring conductivity in a solution, we have to be aware of this right here. Sorry guys, our measurement range and this cell constant value. Sorry. The cell constant is calculated by dividing the distance of these electrodes, so either 2 electrodes or 4 electrodes, by the area of the plates, and you get some value. You get like a 0.01, a 0.02, a 0.1, a 0.2, a 1.0, a 5.0, a 10.0, there's some numeric value. This numeric value is what's inputted into the analyzer, and in the electronics, it does the calculation. So one thing that we can do with these sensors is if we shorten the distance between these 2 ions, between these 2 measuring plates, more ions are going to be able to travel and make contact, because remember there's an alternating current right now going between A and B. One is positive now, one is negative, and the analyzer at some point flips them. And it's on the ratio in which this is alternated is done at a certain frequency. So one thing that we can do to change the cell constant, if we don't want to add I'm so sorry guys, we don't want to add plates to it, is we do 2 things. We shorten the distance and we increase the area of the cell plates so that we can get a better accurate reading at higher concentrations. So we just need to be aware. If we're in and that's what we do in low conductivity readings, we have a very short distance between the 2 measuring cells and we have a very large surface area, so that in a solution that has virtually no ions present, they have a large area in which they're more likely to be able to make contact with the measuring elements, so we're going to have better accuracy and higher measurement. In solutions with high concentrations of conductive ions, we do the opposite. We actually decrease the area of the plates, so we make them smaller, and we increase the distance between them. We may keep this frequency that the analyzer generates that alternates the current the same, but now the ions have to move longer distances before it can get back and forth. And the purpose of this is so that we don't have the effect of what we call polarization. We want the ions to be able to freely move without bumping into each other or without being stuck and not being able to alternate. between our measuring elements. And this is what we call polarization. If we pick the wrong cell constant for our application, then we're going to get polarization. And what this actually looks like is we're going to measure fine over a certain amount of time, and then at some point our sensor is going to become, our measurement's going to become flatlined. This can happen in a short period of time, or it can happen within months to over a year. So this is very common to see polarization occur that may not, we may just think that our sensor fouled, and we just take it out, clean it, put it back in, and it starts working. Then it actually does it again. The reason why you're able to do that is these are just ions. They're just kind of friction charges on that sensor. So when you take it out, you decharge the system out, you wash all those ions off of the plate, you stick it back in, and it works again. So if we have the wrong sensor, guys, I am so sorry today. I got something that kicked in this AC, got stuck in my throat. If we choose the wrong sensor with the wrong cell constant, we'll have this kind of issue right here. So we just need to be aware. And we also need to be aware, going back real quick, I gave you kind of some values. Just because one competitor's sensor says 0.01 cell constant doesn't mean it has the same range from vendor to vendor to vendor. So we need to be conscious of, when I use this vendor's sensor, what the actual measuring capabilities of that particular vendor sensor is versus another vendor's. Because when you go to extend the ranges of your sensor, you either have to A, change this multiplication factor, or you have to change the frequency output that the current actually alternates back and forth. And some competitors or some vendors, Yokogawa is one of them, what we do is we change the frequency. So automatically on its own, the analyzer knows, okay, I get to this point and I have to change my frequency, so it increases how quickly it alternates that current to extend the range. So just be cautious of, when you go to find a new sensor, that you just don't go, okay, I need one that's got a 2.0 and a 3/4 cents connection. Make sure that you know that your 2.0 is actually this measurement range. Or you could fall into a trap where you get a sensor that someone else's 2.0 is not 0 to 2000, but it only measures 0 to 400. You're actually measuring at 800, and then you have polarization that takes an effect in your sensor. So just be conscientious of that. Alrighty, so best practice for cleaning and calibrating. Let's see how long we got after all my fix there. Sorry, you guys, it was like 30 minutes. We're at the 30-minute mark. So do's and don'ts. Here's what we say. Just like your pH, even though for the most part these sensors that you're using are metal, they're probably stainless steel. Some of them applications are going to be Kynar or that Teflon material or PEEK. Always clean them and always rinse the cell. Always use fresh calibration buffer solutions if you are using solutions. And then always clean your beakers before you put your calibration sensors in them. That way, if there was any soap or something else that would have a conductive charge to it, conductive ions if dissolved in solution, doesn't interfere and, contaminate your buffer solution. And then what we'd say don't do is, if possible, we want you to do air calibrations below 10 if you're in ultra pure water, and we'll show you why in just a moment. So most people nowadays are kind of moving to a pre-made solution, a NIST standard solution. These again are Hamiltons that they offer. These are pretty accurate. They have expiration dates on the bottle. You're going to use them where you pour sample, use it, and then toss it, so you only use it once. But they have a really great one. If you're going with pure water, ultra pure water, and you want to calibrate, they actually have a 1.3 microsiemens solution that's stable for up to 1 year. So here's just some examples of the ones that they have to offer and the accuracy of them and how stable they are. So these are good spot checks. If we're comparing our online to a lab meter and they don't match, just like with pH, you start pulling out those pH buffers. Conductivity has the same capabilities of it. The problem with your ultra pure water your low conductivity, the minute you have, like he said, carbon dioxide can seep in through that membrane and dissolve. You're going to have what's formed carbonic, the carbon dioxide will dissolve and form carbonic acid inside your water sample. So you'll get a false high conductivity reading just because of carbon dioxide increase. So if you are doing grab samples for your ultra pure water and using that as your calibration, it's not recommended to do that. We actually prefer you to do an air cal instead. And it is literally as simple as most analyzers have the ability to do it. You just need to clean the sensor, make sure it's dry, make sure that there's no water trapped in any of your measurement elements, and do an air cal. This is very accurate and helps you. So anywhere where you're below 10 microsiemens, we actually prefer you to do an air cal. You can also do a solution cal, but an air cal is most accurate. When you're calibrating that inductive sensor, remember it's like a transformer. It generates a magnetic field. So if you just have a beaker and you place that donut and it's touching that beaker, if you try it, measure, put it in there with water and have it sit against the glass beaker. Now take it and put it directly in the middle. Hold it still in the middle. You'll see that the same exact water sample will have a different conductivity reading. And this is because the glass beaker affects the magnetic field that the sensor generates. So you kind of construct the magnetic field and the process that it flows through it. So just be aware when you calibrate it that you have it in the, like where it's not being, the field's not being bothered. The best thing that I can say with inductive, if you don't do air cal, literally just stick it in your pipe and do a calibration in place in your pipe. Whether it's got a sample that's running through there, you can do a sample cal, or if it's dry, do an air cal inside your pipe, because then the analyzer will auto-correct that installation factor, that cell constant, what we call, that's on that sensor, to what the pipe process around is also doing to the field. So that is our personal best practice of it. So just a couple slides on troubleshooting and what could be wrong from our point of view and what to check, and then we'll get to the Q&A. Most common complaints that I hear is about unstable measurement. Most commonly what we've seen, if you have an unstable measurement, is air bubbles could be trapped inside your contacting sensor. Remember, you've got two cells. If you've got an air, and most of them are kind of like flow-throughs, they have holes that somehow they go, the sample passes through. If you have air bubbles trapped in there, you're going to get low readings. If you're in your pipe and your sensor, just like a pH probe, goes out of sample, you're going to get low readings. So that could be your installation's wrong, or simply the flow from the process is creating bubbles inside the measuring element. Sometimes if you get a wrong measurement is what we hear a lot. It's supposed to be this, it's this. Your sensor could be dirty. You could have the temperature compensation either turned on, turned off incorrectly, not set the same way as your lab meter that you're using to compare it to. Also, cabling. Eventually, it does go bad. So most of the time, cabling can eventually cause wrong measurement errors as well. So when a process occurs, this is what we normally do. We check your cell condition, pull it out. I check to see if it's dirty, if it's coated, corroded, if the cable connection's wet, just like we do within pH, make sure that there's no nicks, there's no frays from pulling it through the conduit. And then I check the analyzer programming. If you get a brand new sensor, you stick it online, and you've put that cell constant. Remember, with contacting conductivity, you have to put in a cell constant, multiplication factor, 0.1, 0.01, 1.0, 10.0. If it's off by a factor of 10, your measurement reading is, it's a good indication that there's something wrong with how I programmed my cell constant. And it could be as simple as the analyzers normally auto change from micro to milli Siemens. If we put in a cell constant, we put it in wrong, it could be that, and that's most commonly what we see, and those are most of the time where the problems are, is at just startup. Other times, what we'll look at is obviously process changes. This is when we have problems where I just stuck this in and it only lasted a week. Why did a metal sensor just last a week in a process? If it was something that wasn't high temp sensor that had high temps, put in the boiler drum, steam drum, the O-rings fail, the epoxy coating, the epoxy sealing inside the sensor is not meant for high temp, those will fail. So we look at that kind of stuff. And again, this is the biggest thing with inductive conductivity, is that insulation factor. Remember the pipe and vessel installation, we need to make sure that you have a minimum. We prefer with ours a 1-inch clearance around that donut, because at the 1-inch mark, it's not going to affect the magnetic field that the sensor generates. But if you're always got caution, just stick it in and do a process cal, and that will autocorrect in the analyzer the cell factor correctly. Another thing to look at with inductive is installations. Okay, here is the donut and it's stalled. It's a big pipe, but it's possible that the donut, the sensor itself, is not in the process flow. It's possible that it's installed in air bubbles. So we need to make sure that the sensor is actually installed in sample, because if sample does not pass through that donut, then the solution cannot pick up a current, electric current, and can't drop it off, those ions that are present in there. So we don't get a good conductivity reading. Same thing with those contacting styles. And this is just to show you one style of kind of a flow-fitting sensor. Some of them have holes in the bottom and then a outlet on the arm. Some of them look like this, where they have holes through the bottom of it. So we just need to make sure that we install it where the flow is going to go through, the flow fit the sensor itself correctly as well. So in this application, we recommend you doing the 2 on the far right, going on the elbow, going upwards if you have to. That way the flow goes in the sensor and out the sensor correctly, so you get the process solution to pass by this contact measurement elements as well. And then this is one that I have come across with in the past couple weeks. Customer couldn't figure out why the sensor wasn't working, and they sent me a photo of it, and I don't know if you see it there, but there's internal O-rings in these sensors itself, and they have certain pressure ratings. So if we exceed those pressure ratings, or even if there's chemical attack on the internal O-ring, that's going to cause you measurement errors, because in this particular case it wasn't sealed, the electronic side of the sensor, so process was getting upside in there and shorted the sensor. Here's another one. Be cautious of those inductive sensors. Literally, you can put one of those inductive or electrodeless sensors in line and it will last probably years. But they do fail over time, so it's good practice just to visually pull it and check it. I don't know how frequently people do it, but I would say probably minimum once a year, or you may have standard procedures that when that go down, go check it just to be case, because they do give away. And these are pictures of 2 last year, where they finally failed after 10 years, and they said it's not working. They pulled it out and sent it to me, and that's the condition that the sensor was in. There's a reason why it's not working. That's supposed to be brown, or supposed to be like a peak gray material instead of, or I guess a tan material instead of black. And then the same thing was process physical was attacking the sensor material. So if peak is not compatible, like in the sulfuric acids, we need to make sure that we use Teflon. So just be sure to check them and make sure we pick the right materials for the right sensors. So with that being said, that is 40-minute mark, and we should have 10 minutes for Q&A, because I started having coughing fits in the middle of that. Sorry, guys. But that is the level in which is enough for conductivity for the most part for people.
Thank you, Sherlyn. It's now question and answer time. So if you haven't written your question, please write it now. Sherlyn will read off each question one at a time and then give the answer. Sherlyn?
Alrighty, just waiting for the questions to come in here. Okay, that one is just a partial question. It just says not for wastewater, question mark. I guess I would need to know at what point in the presentation that was chosen for. If you're referring to is contacting style ideal for wastewater, you can use it in wastewater, but make sure you use a 4 electrode and probably one of the higher cell constants, the 1.0 or the 10.0, because of the range in which your wastewater is going to be. But ideally, if you can use that inductive sensor, you're going to stick that puppy in your wastewater, especially if it's just like municipality wastewater, your wastewater out into your plant. And that should last, assuming that it doesn't get electrocuted by lightning, the system doesn't, should last years. Yeah, conductivity is a lot more simpler than pH for the most part, and less troublesome and headaches. So we're here to help with any questions. Even after this, if you've got any problems that you may be seeing, feel free to ask me questions, and I can take you as far as what I think the problem could be, even if it's not my instruments. Point you in the right direction to look at. So
Okay.
It looks like that's all the questions.
All right. Well, thanks so much, Sherlyn. And if you do have some questions after this, you can email Sherlyn. For more information on water treatment in general and like conductivity specifically in applications used for monitoring RO or ion exchange or different parts of a treatment scheme, we have many different training sessions and seminars, and we also have online training, and we can train either at our place or your place, whatever makes sense for you. We also do technical services, so if there's anything that we can provide that will be of service to you, please let us know. Thanks so much for attending. As you exit, if you'll just take 10 to 30 seconds to answer the 3 polling questions, and that gives us feedback on how valuable this was today and how satisfied you are. Thanks so much. We'll see you next time.